Today I'm going to be talking about developing equipment and methodology for brake and tire wear generation, collection, and analysis. This work has been ongoing in the SRF community, and I'm excited to share some initial results. The motivation for this non-exhaust emission work has stemmed from the variety of projects that the SRF has been and is currently researching. This list gives a very brief overview of the projects that the SRF has been researching the past number of years that it's been around, involving fuel transportation efficiency, future fuels, as well as acoustic and exhaust emissions. And now moving into the non-exhaust emissions. As you can see that this will become a very important issue to tackle as we move forward. Here I have a quick graph that looks at both the measured and projected emissions by kilometer. The projected emissions start at 2018 and go forward, and the measured emissions are 2018 and back. And what this shows is that on-road emissions for diesel and petrol exhaust is actually declining. So we're seeing this gradual decay of emissions, whereas the non-exhaust, both brake and tire, as well as road surface wear, is not only increasing, but projected to increase even more so as we move more towards a more electric fleet, a more heavier fleet. This has really led the SRF to be interested in these non-exhaust emissions and trying to improve the non-exhaust emissions that are on the road. A test rig was created that generates tire particles by pressing down a piece of a tire onto this surface. Right now we're using sandpaper, but this can be changed out to different abrasive surfaces, coarser, finer sandpapers, etc. The particles then come out and are extracted into this tube, which then goes into an ELPI instrument, which measures the number of particles and the size of particles and the mass of particles that are coming out of this system. I will mention here that this is sitting directly behind where the tire is interacting with the surface and therefore has the highest capture rate. There does need to be a few tweaks on this, and I'll cover that later on. We've been able to use this setup to give some initial results, primarily revolving around mass. So looking at the mass that's been emitted from these tire particles that we've tested so far have given very interesting results and have been very interesting for the initial part of this study. What we've seen with this is, so this graph here is looking at the mass of the particles versus the time that we've been pushing the tire onto the surface, segregated by PM10, PM2.5, and PM1. What you can see here is that there is a fingerprint region in the PM10 category. So we can see that there's variations within the sensor. PM2.5 does have a bit of this fingerprint region, but PM1 does not. It's not on this scale, at least, and I'll come back to that in a minute. However, this is very interesting and very encouraging first results. There are improvements that can be done within the testing rig itself to help magnify these emissions. This will be things like directing the spinning of the wheel the opposite direction, so we're getting a higher fraction of the particles coming out, as well as having a narrower inlet so we're not diluting the sample as much. So again, these are just initial results. Interestingly though, if we overlay the fingerprint region from the pressure profile, so that's the overlay here in orange, what you can see is that the pressure points actually line up with some of the higher peaks in particles. So I will say these time series aren't aligned perfectly right now, but what we can see is that we have a contact point with the sandpaper from the tire. We see this increase in mass that's being emitted. With those direct contact points with the tire and the abrasive surface, we're then able to get this fingerprint region, as I mentioned before. There is a lot of future work that can be done with this tire rig project. As I mentioned, we're just getting off the ground running with this now. In future studies, the main changes that we'll be making will primarily be changing the sampling mechanism. So again, as I mentioned, we're going to be rotating the tire in the opposite direction to get a higher fraction of the particle. We're going to be changing the wear surface, so we'll have a smoother sandpaper as well as a more abrasive sandpaper, so then we can compare and contrast those. From this, we can then calculate the wear rate of the sample. This will be something we'll be working in collaboration with. We can then align the pressure of the tyre time series to the LP time series. So then we can give a mass or a number emitted versus the pressure. What this information can do is then showcase how the pressure is influencing both the mass and the number of the particles. And if we can then decipher which of those is being affected more by an increase in load, slip wear, or the differences in tire surfaces, being that we'll be able to correlate the surface of the abrasiveness to the particle size and mass that's been emitted. So that was some of our initial results from the tyre rig sampling. As I mentioned, we have a lot of work to do on this, but now we are up and running, we're ready to go, and the initial results are quite promising. We also have a lot of data on the pre-wear analysis, and I'll discuss that a bit now. And this also leads into what can be done for future studies as well. Another component to this tyre wear analysis is doing the elemental composition of non-worn tires. So these are new tires that we've then analyzed using ICP-MS to understand what sort of elements are being put into the tires during production. What this can then do is then lead us to understand what elements can then be used for emission studies on the road. If we know that these elements are in the tires, we can then start to identify if we're measuring non-exhaust tire emissions or if we're looking at some other source for on-road measurements. So how this analysis has worked so far is that we've digested new tires, about 5 to 10 milligrams, and then we've run ICP-MS on this. We're trying to build the largest database that's available right now. Right now we just have a very large database, but we're hoping to have the largest database. And we currently have about 40 samples that have just come in that we're then going to be able to use to help bolster this as well. We can then do this elemental composition for the worn tires as well. We have not done that yet, mainly being that we need about 10 micrograms of tire wear or brake wear to actually run these different tests. Acquiring this much sample is a bit of a challenge and something that we're going to need to be creative in order to get. Primarily, we might not have as high resolution in the size fractionation of it, so we might need to just do we might need to do a more granular cut point, so PM10 and PM2.5, rather than having the 15, 16 different cut points that we have on the LP that's currently available to us. We can then also look at this information by manufacturer. Right now we're just looking at manganese. By manufacturer, we've coded these so you wouldn't be able to guess potentially who these manufacturers are. But what we wanted to do is pick out what different manufacturers would have as their metal composition that they would all have. And interestingly though, there seems to be one outlier that has a lot higher manganese than the others. So if you're trying to detect for this in the real world, understanding those limitations might be really important going forward. But again, we can then do this by manufacturer, by all the different elements, and being able to understand what their compositions are that way as well. Another analysis tool that we have access to here is SEM imaging as well as elemental mapping. What this information can do is give information on size, shape, and structure of the particles that have been deposited onto different substrates. We can look at the composition of the emitted particles, whether they are elemental in nature, if they've agglomerated in nature. We can also measure these particles when they're sitting in this instrument, so we can get some sort of information on their length as well. As I mentioned, these particles are deposited onto filters, and that can be whether it be on the LP instrument that we have, where we have high resolution of size fractions. So this is looking at anything from nanoparticles up to 10 microns at a much higher size resolution. Or it might be that we are looking at more rough cut points. So this would be PM10, PM2.5. And the reason we would want to do this is to keep it consistent with our elemental analysis. So if we're having cut points of PM10 and PM2.5 for the elemental analysis, we would want to keep some consistency there as well. We can also do things for non-size analysis, so we can take particles that have just been sprayed in the tire rig where we can scoop them up and put them onto a filter and look at those as well. So these would be ones that aren't sampled, and we can then compare them with the ones that have been extracted using our extraction system. This can be for individual particles as well as for scans of entire filters and substrates. So we can look at particles individually, where we can map their elemental composition, or we can have our instrument, our SEM instrument, scan the entire filter that's been deposited onto. Just in the box here, just have a quick overview of how scanning electron microscopes work. But there's a variety of different information that we can get from these tools. Again, looking at their phases, their topography, crystallography, and their different magnetic fields. So we have the option to tweak all of these different things so we can get a variety of different information from this. To give an example of how these particles look under the microscope, this was a filter that was taken by David O'Lowlin, and so what this looks at is a tyre particle, and we know this is a tyre particle, and you can kind of see the dinosaur shape in this as well, where we have an agglomerated particle that has all sorts of different elements in it. We can see that when we look at the elemental mapping. So here on the left-hand side is a total view of all the different elements that's there. And then on the right, we have this fractioned out by the different particles. So we have silica, aluminum, oxygen, and calcium. And in calcium, you can see where there's the really highlighted versions. That's a big calcium chunk that's in there as well. So you notice we also have the size in the bottom, but we can do a more accurate assessment of the length if we are able to use some of the other tools that we have access to now. Just to give an idea of a second particle, what they might look like, again, they have a bunch of stuff on them, lots of characteristics. Again, at different length scales here as well. And then again, we can look at the elemental mapping. This one has a bit more color to it. So we have, again, the calcium chunks that we're seeing. And so here we're able to see that as a whole. In addition to the work that we're doing here at the University of Cambridge, we are part of more broader collaborations with our TyreWare specifically emissions. We are involved with a project with the Tyre Industry Project. There's a lot of crossover with people involved and the companies involved with TIP as well as here at the SRF. We're going to be using Karlsruhe Institute of Technology for their facilities in order to generate particles so we can look at on-road emissions that way. And we'll be giving an in-depth analysis of one specific tyre that TIP has chosen. And so with that, we'll be able to, again, dive into the LP and the LPI particle size distribution, and we'll be able to do some of these offline analysis using SEM to look at the morphology with that project as well. We'll also be able to look at both the solid and non-solid component using this thing called a catalytic stripper. And what that does is it allows us to remove anything that's volatile from it, and so we can just look at the solid particle beneath that, which might be of interest as well. In conclusion, the Center for Sustainable Road Freight is really leaning into these non-exhaust emission studies, both with the work that's going on within the Center for Sustainable Road Freight and collaborating externally. We are looking at both on and offline analysis to understand the size, mass, and morphology, as well as elemental composition of these emitted particles. We have new work with the Tyre Industry Project, where we're able to help quantify and correlate these emitted particles as well. We can then use all of these particles in toxicology studies, where we can understand their interaction with our respiratory system in general. This work is very interesting to me, and I'm very excited that the SRF finds it valuable as well. And with that, I would like to thank you, and if there are any questions, I am happy to take them.